In today's video, we will understand how does a Kalina cycle power plant work. Here we will mainly investigate what's the reason behind its high thermal efficiency compared to the conventional power plant cycles. So let's start. The major difference between a conventional cycle and a Kalina cycle is that Kalina cycles use mixture of two fluids as its working fluid. And most commonly used working fluid in a Kalina cycle is mixture of water and ammonia. So what's the advantage of this? Why should we use a mixture as a working fluid? To get answer for this question, let's see temperature entropy diagram of a conventional cycle and a Kalina cycle. Here it is. The first one is a TS diagram for a conventional Rankine cycle, and this is TS diagram for a Kalina cycle. So here you can notice a major difference between these two. In a Rankine cycle, during phase transformation, temperature doesn't change, it remains same. You can see during heat addition process 2 to 3, temperature doesn't increase during phase transformation. Similarly, again in condenser, the process 4 to 1, the temperature doesn't change due to phase change. But this is not the case with the Kalina cycle. Here even during phase change, temperature changes. You can see it over here. During heat addition, temperature rises, and during heat rejection, temperature drops, since we are using a mixture as a working fluid. And this small deviation in thermal cycle makes all the difference in Kalina cycle. This will explain why Kalina cycle has got much higher thermal efficiency compared to a Rankine cycle. Simply because of this reason. Efficiency of a Carnot engine can increase due to two reasons. First, when temperature at heat rejection site decrease, or when temperature at heat absorption site increase. So in order to use this formula, we will take average heat addition temperature and average heat rejection temperature for both the cycles. For a Rankine cycle, average heat rejection and average heat addition temperature will be like this. Average heat rejection temperature is same as the condenser temperature because temperature is uniform during the process. And roughly this will be average heat rejection temperature. And these two average values for a Kalina cycle will be like this. You can see it's much wider compared to a Rankine cycle. It has got higher average heat absorption temperature and a lower average heat rejection temperature. So obviously it will have a high thermal efficiency. Now let's see how this cycle is implemented in actual case. How does it work practically? First we will start with a very simplified Kalina cycle power plant. It has got four major components as a Rankine cycle: a steam turbine, a condenser, a compressor, and a boiler. When mixture expands through the turbine, power is generated over here. But the main difficulty in a Kalina cycle is over here, at condenser. Because right after the turbine, the working fluid will have almost 70% of ammonia by weight. Now, according to the phase diagram, when concentration of ammonia is high, the condensing temperature is very low. You can see it here. When concentration of ammonia is 70%, the condensing temperature is really low. If you want to condense such a fluid, you have to supply a very low temperature coolant through the condenser. That is not practical anyway. So what we will do, we will alter this concentration. We will try to decrease concentration of this ammonia with help of a device called separator. What this separator will do, it will separate out the working fluid to a lean mixture and a rich mixture. And this lean mixture, which is having almost 30% of ammonia by weight, will mix with the exit fluid at the steam turbine and will produce a mixture of almost 40% of ammonia by concentration. Now if you check at phase diagram, such a mixture will have much higher condensing temperature, almost over here. This can be condensed using a regular cooling water supply. Now the condensation process is over, but we have to regain the original ammonia concentration in other parts of the cycle. For that purpose, rich mixture from separator will get mixed with the incoming stream and the working fluid will regain its original concentration, the 70% of concentration. If you check temperature entropy diagram of a Kalina cycle carefully, you can notice one thing over there. Temperature at exit of steam turbine is much higher than temperature at inlet of condenser. Or temperature at 0.4 is much higher than temperature at 0.2. You can see it over here. But this was not the case of the Rankine cycle. In Rankine cycle, these temperature levels were in other way. Temperature at 0.4 was lower than temperature at 0.2. After this 0.4, we are rejecting heat to the surrounding. And after this 0.2, we are absorbing heat from some external agency. So why can't we supply some amount of heat from 0.4 to 0.2, which will save some energy and will obviously increase the power plant efficiency. That's exactly what we do here. We are introducing a heat exchanger called recuperator. And function of recuperator is to transfer some amount of heat from 0.4 to 0.2. This is obviously possible because temperature at 0.4 is higher than temperature at 0.2. And thanks to the recuperator, you need not to supply same amount of heat input you supplied before. So recuperator heat transfer increases thermal efficiency of a Kalina cycle to a much higher level. And all these things prove that Kalina cycle is a power plant technology